Okay, I'm going to go ahead and do a sample project here for your review. Hopefully this will help you out as you're doing it. One of the students sent in a bill. So let me go ahead and show you that bill, that invoice first. All right, so this is the invoice for the facility. And so what we're going to start with, it's just showing you, and this is pretty typical of bills, it's going to show you a monthly electrical history. What I did here first is I went ahead and added up the 12 months. I found that over the course of the year, they used 29,377 kilowatt hours, divided that by 365. I could have taken the monthly average, divided it by 30 and a half, and got approximately the same number. But in this case, they're going to be using 80 and a half kilowatt hours per day. So it's a pretty large facility. Remember, the average usage for a suburban home is about 30 kilowatt hours. So this is almost triple the size of a traditional home. And as we'll find out here a little bit later, I think this is actually a business or a farm. Not quite sure exactly. We'll go down through, there's all the different rates. We're not that concerned at this stage because we're just designing the facility. We're not really worrying about what the payback period is or the like. And so that's given us some key information. It's given us usage and it's given us an address. All right, so we'll jump from there. The next step I would do is I would go ahead and go in and look at this address. So the first thing I do is go into Google Earth, and I went ahead and typed in this address, and this is what the facility looks like on Google Earth. In fact, if I scan out a little bit, you'll see it really looks sort of in the middle of farmland there. I can't really tell, and of course the student's not on the call at the moment, what this is. It looks like that might be a pen of some sort, so it might actually be, I don't know, some sort of animal processing facility, feeder lot, something like that. Anyway, but it looks like there's a large barn here with good, if I orient this to the south, all right, this is the southern exposure. So we've got this oriented north-south. I'm assuming there's not going to be any zoning issues because it's out in the middle of nowhere. We could come in and we could go ahead and put it on one of the buildings if we wanted to. We've got some roof space here. There are ways of calculating that. But let's assume that we're going to use a ground-mounted system because there's so much land here and they probably could do with some covered parking or something of the nature. So what I've determined here is we can set it, by doing a ground-mounted system, we can set it at whatever orientation is ideal. Usually that's going to be true south or 180 degrees azimuth. And then I can shoot it, put it at whatever altitude or angle is going to be ideal because I don't have to worry about the roof. So that's usually at this latitude. I find this is at 40 degrees north latitude. I get that down here at the bottom. So you're going to find that the angle is going to be somewhere between 28 to 35 degrees. So if we say 29 degrees, that's going to give us pretty good numbers there. So then I'm going to jump into PV watts. The PV watts calculator is going to let me know I can set system losses, I can set the side, again, that a size, that's for financial information. But at the moment, I'm only worried about azimuth and altitude or angle or tilt. Okay, it comes up defaulted at 20 degrees and 180 degrees. So if I jump over just using the defaults, I'm going to find that on average, we get about 4.81 hours of insolation each day. If I want to mess around with it a little bit, I can type in 29 degrees, and I'm going to find that I get slightly better. I'm going to get in the neighborhood of 4.93 let's just try it and see if I can get even better. Let's try 31, see what happens. It was 4.91 if I remember right. And now it's 4.94. Okay, so let's keep it at that, 4.94. I'm going to make a note of that. 4.94 hours. All right, and then we're going to have to assume, we're going to have to determine what our D rate factor is. So we can go ahead and say, all right, our inverter, let's assume we're going to have about a 96% efficient inverter. So that's going to be 0.9. So that's going to be about a 6% or 4% D rate on that, 2% on voltage drop. So that's going to be 6. Throw a couple more in. So let's just say, no, if it's a string inverter, we're going to have plus or minus 5% for the various panels, because everything in this string is going to be plus or minus 5%. So that's going to take us up to 11%. All right, so let's say 11% D rate or an 89%, because I'm going to do this one using a string inverter just so that we can do our string calculations, things of that nature. So if I jump in and let's go ahead and size the array. So if you remember, the way we size the array is we take our daily load, which in this case I've determined is 80.48 kilowatt hours per day. And we get, what did we say, 4.94, if I remember right, hours. That's kilowatt hours per day. And that's going to give us 80.48 divided by 4.94 gives me 16.29. So if it were 100% efficient, I would need a 16.29 kilowatt array, but we've determined that it's only 89% efficient. So we divide that by 0.89 and we need an 18.3. So I need an 18.3 kilowatt array. All right, so at this stage, why don't we jump out and we're going to go ahead and do a little bit of shopping. So we know, I'm going to make note of this thing here too, 18.3 kW. That's if we want to service 100% of the load. So I'm going to go ahead and go to my distributor of choice, and I don't want to say that you have to use these guys as a distributor, but I find their websites easy to navigate. So that's what I'm going to be doing with it. I'm going to look first for solar panels, and I'm going to assume that these guys are legitimate, that all of their panels are high quality. So I'm not really too concerned with the panel manufacturer. I'm just going to go with what's the cheapest price per watt. So I've sorted on price per watt, and I find their Trina Solar 415s, they're charging 49 cents per kilowatt hour. I could go with Canadian Solar 390s, that's 50 cents per kilowatt hour. So let's go with the Trinas, okay? I'll go with the Trina, and I'm gonna make some notes here. Trina, it's 415 watts. And we're going to need to know some of the specification details on the Trina solar panel. Some of them are very easy to find. We're going with these guys here. So I need to know what is the, I'm just going to write down the VMP is 40.9 volts. The VOC is 49.6 volts. And then the ISC is going to be 10.66 amps. All right, yeah, they're 20% efficient. I don't care about that. They are 144 cells. These must be split cells, 72 split cells. That sounds about right. Okay, 25-year power. But then I also need to know what are the temperature coefficients. And here it's going to do that under the data sheet. And hopefully this is going to show up. Not quite sure how the sharing here does, but if it doesn't show up, I can see it anyway. So I'll write those down, but the temperature coefficients are temperature coefficient at VMP is 0.36% per degree Celsius. And at VOC, it's 0.26% per degree Celsius. I'm going to need those for the string calculations. All right, so I picked that. I'm going to jump back in just in case that screen share was messed up. And I'm going to look at an inverter because the two things I need first are the panels and the inverter. So I selected my panels. Now I need to go and find what kind of inverter. This is a large system. Remember, it's an 18.3 kW system. And we're going to do a grid-tied system. I'm not going to do any hybrids or anything like that. I'm just going to do a straight grid-tied. So this is saying 8 kW or bigger is considered commercial size. So just to see what they might have here, they've got a Fronius 15. That looks like the largest one there. Or I could go with 2 Fronius 10s. Let me think how complicated I want to make this. Yeah, let's go ahead and go with 2 of the Fronius 10s. We're going to make this a complicated unit. All right, so I've got Fronius, and that's just the manufacturer, 10 kW inverter. And what am I looking for with my 10 kW inverter? Well, I'm looking for what is its minimum, what is its maximum. So the operating range here looks like, let's make sure I'm in the 10s. Here's the 10. 80 starts up at 80 volts and it goes to 600 volts. Now it's also telling us that the sweet spot, the part that it likes to be operating at, is going to be the MPPT voltage range is between 220 and 800 volts. Oh, that's quite a range. Okay, so nominal input voltage 415, that's hopefully what it's going to be operating at. And then the other thing I wanted to know is what is its efficiency? And it's showing that the maximum efficiency is 96.7%. Remember when I did my D-rate, I estimated that it was going to be at about 4% in efficiency. So it looks like I'm pretty good there. All right, so I've got that. Now I can go ahead and do my string calculations, I think. What I'm going to need to do is have two inverters. So let's see if, well, the first thing I'm going to do is I'm going to figure out what is my, how many panels do I need? All right, so that's fairly straightforward. I've got my array size. I divide that. I know that the panels are 415 watts. So I simply do that division, 18.3 divided by 415, gives me, looks like I'm going to need about 44. Let me just double check that. 18,300 divided by 415 gives me 44 panels. All right, so I need 44 panels. Well, that's nice. So each array, it looks like, because I'm going to have 2 different arrays, essentially, because I'm feeding 2 different inverters. I'm just going to assume that each array is going to be 22 panels times 2. Okay, So this is how I've determined. I'm just balancing. You don't have to balance the arrays, but I'm going to do that just for convenience sake. All right, so then what size strings do I need? All right, so I've got, how do we determine the strings? Well, the first thing we do is we take the difference in degrees Celsius from the coldest temperature, because I'm going to do the maximum number of strings in a string. The coldest temperature ever experienced in Illinois versus standard test conditions. So in order to determine that, first thing I need to do is jump in and, whoops, that's not the one I want. That's the one I want. Okay, I had looked it up before. What's the coldest day ever in Loda, Illinois? And I found out the lowest temperature in Illinois was minus 36 degrees Fahrenheit, unfortunately, and that's the lowest temperature ever. Well, unfortunately, Fahrenheit's not going to help us, but if I say minus 36 degrees, that tells me that it's minus 38 degrees Celsius. So that's the coldest. While we're at this, why don't I try and find out what's the warmest day ever? And it's going to say the warmest day ever, 48, the average high, low to weather. Let's see, sometimes it's the highest temperature on this state, hottest day ever outdoor, 1954 was 117 degrees. So we jump in here and we say 117 degrees. Man, Illinois is a rough place to live. Okay, so coldest is minus 38, highest is 47 degrees Celsius. So we've got our high and our low. So I'm going to jump in here and I'm going to go ahead and go back to my whiteboard. And I take the delta. So for the coldest day, minus 38. 25 is standard test conditions. The difference, or the delta, is going to be 38, which is negative, plus 25. So that's 63 degrees Celsius. So that's our delta, the difference between minus 38 and positive 25. I know the temperature coefficient we're going to do at VOC because we want to do worst case scenario. So that's going to be times 0.26% per degree Celsius. Remember, I got that off of the specifications for the solar panel. So I would take 63 degrees times 0.26 equals 16.38. So what that's telling me is that on the coldest day ever, the panel is going to generate 16.38 degrees or percent more voltage than it would under standard test conditions. Well, the voltage, worst case scenario, or best case, however you want to read that, is VOC, which is going to be 49.6 volts, which is at VOC, times, now remember it's more, so it's going to be 116%. And when we convert a percentage to decimal, we just move it by 2 places. So I can do times 1.1638. So at this point, I'm going to say 49.6 times 1.1638 equals 57.72. So 57.72 volts. So on the hottest day or coldest day ever, this panel or this panel could generate 57, almost 58 volts. Well, what was the maximum the inverter can handle? We looked that up and we found out it is 600. So I would take 600 volts, which is the maximum the inverter can handle, divided by 57.72 volts, which is the maximum under any condition our panel might produce, divided by 57.72, and we get 10.39. All right, so we're getting 10.39. Okie doke. Hey, Ursula, I'm working on your problem. We've already determined the size of the array. Here, you can review that in the video, but I'm working from a 18.3 kW array. Okay, so we've determined that we can put 10.39 maximum per string. Now, I was kind of hoping we could get 11 because we determined that 22 in each array, we're going to do 2 arrays here. So that would have been quite easy. We would just go 11, 2 strings. But at this point, we're really going to have to go with, I could still do 11 because this is quite, but the permitting process might not allow me for that. So I might go back and select a different panel if I wanted to play around with that, but this is going to make it a little bit more complicated. All right, so we've done the maximum in a string. So how do we calculate the minimum number in a string? Well, in this case, we've determined that it was 47 degrees Celsius was the maximum temperature ever at that site. 25 degrees Celsius is standard test conditions. So the delta between those two is going to be 22 degrees Celsius. But remember, for the minimum, we've got to also add in, because the cells are going to be hotter than ambient air temperature. We determined this was going to be a ground-mounted system, so I'm going to add 25 degrees. We would add 25 degrees Celsius for a ground-mounted. We would add 30 for a ballasted roof-mounted system, and we would add 35 for a flush-to-roof mounted system. So that's going to jump us back to 47 degrees Celsius. So we've subtracted 25, we've added 25, we're back where we started. So then we'll take this times the temperature coefficient at VMP, normal operating conditions, which when we looked that up on the panel spec, it was 0.36% per degree Celsius. And we do the math there, and it's going to be 47 times 0.36 equals 16.92. So what that's telling me is on the hottest day ever, this unit, this system is going to produce 16.92% less than it would under standard test conditions. Well, what is the voltage under standard test conditions? That's the VMP. So I'm going to start 40.9 volts, which is my VMP. And I'm going to multiply it times 100% minus 16.92%, which is going to be 83.08 or 0.8308. So I take that 40.9 times 0.8308, and I find on the hottest day ever, this panel, that doesn't seem right, times that, should be less. I got a number bigger. 40.9 times 0.8308. Yeah, there we go. 33 point, well, really 30.98, almost 34 volts. So on the hottest day, this will produce 34 volts. And on the coldest day, it might produce almost 58 volts. You notice there's quite a range between those. So I know what the voltage is. So I'm going to take the minimum startup. The minimum startup of the inverter was 80 volts. Divide that by 33.98 volts. And I'm going to know that I need 3. I need 3 panels minimum. I don't even have to do the math on that. So that's minimum. And 10, remember, we're going to have to round down. So it's going to be 10 max. 10 maximum, 3 minimum. So those are our string options if we go with this particular inverter. Okay, hopefully that makes sense. All right, so then I figured out my string calculations. So what do I need to do here? Let me write down 10 max 3 min, because my memory may not be good. One of the nice things about Fronius is that 80-volt startup gives us a lot of flexibility. In the old days, we used to have situations like if it were 250-volt startup, I might find that I couldn't, my minimum was actually greater than my maximum, and that happened occasionally. All right, so what are we dealing with here? Well, let's talk about only one of the arrays at a moment. So we've said, okay, here's our array, and we know we have 22 panels. We know our strings cannot be more than 10. So if it were 11, I could do 2 strings. In this case, I'm going to have 3 strings. All right, well, 3 doesn't go into 22. 3 does go into 21. So we have to decide, do we want to undersize this or oversize it a little bit? Well, 3 also goes into, what's the next one, 24? So I could have 3 strings of 8 or 3 strings of 7. So why don't we just assume that this particular facility is going to grow in size? So let's go with 3 strings of 8. So I'm going to oversize it a little bit. So now there are 3 strings of 8 panels. All right, well then one of the things I'm going to need to check is to see, can I run these strings? Well, let's just do it with a standard combiner box. I won't even check that. All right, so if I come into a combiner box, so this is my combiner box. So I'm only going to run 1 string into the inverter. All right, so this is the PV source circuit from the panels to the combiner box. So let's go ahead and size the wire for that. Okay, so how many amps? How many amps are we going to have required for this? Well, when I looked up on the panel, I found that the amps, the ISC was 10.66 amps. That's ISC. Remember, when we hook up things in a string, we find that the voltage increases, but the amps do not. So, so each string is going to have 10.66 amps ISC. That's the worst case scenario. It's actually going to have a little bit less than that if we look at IMP. But the NEC requires that we multiply this times 1.25, which is our safety margin. So that's going to tell us that we have 10.66 times 1.25, and that's 13.325. All right, but then additionally, the NEC says for solar, we need to add in another 1.25 safety margin, because remember, these numbers are at STC, which is 1,000 watts per square meter, but we can have really as much as 1,200 at the solar constant out at the outside edge of the atmosphere. It's around 1,300 amps or watts per square meter. So we can get more amps. So we'll take this times 1.25 and we end up at 16.65. So our wire has to be sized to handle 16.65 amps, even though it's actually going to be carrying a little bit less than 10 under normal circumstances. So before I look up in the table what size wire that is, let's assume we want to put some breakers in here. So we want to put in some circuit breakers as overcurrent protection. Well, what size breaker would we put in? We round up to the next available size. So it turns out we're going to need 20 amp breakers. So we'll have 3 20 amp breakers protecting each of these strings. So if there is a problem, that's going to be taken care of. So now let's jump in and look at the wire size. Remember that these panels generally come with 12 gauge wire. So I'm gonna just sort of look in here. I don't need this particular thing anymore. So let's look up wire gauge table. And we're gonna find that they're difficult to see. See if I can get a, that's easier. All right, so if I jump in here and it's telling me conductor size, this is all copper, 12 gauge is 20 for low voltage or low heat cable, 25 for medium heat, 30 for the highest heat. But hopefully you'll remember in the lessons, it said we really should use only the first column for our wire sizing, because we don't always know what terminations we're going to be, what is the rating for the terminations we'll be using in the equipment, like in the combiner box or in the DC disconnects. So just to be safe, use column number 1, even though we're going to be using PV wire, which is a high heat wire, which in theory could carry 30 amps, but we're going to use 20. Okay, we're going to use the first column. So 12 gauge cable will certainly handle the 16 amps that we're worried about here. So 12 gauge is fine for the PV source circuit. So if we jump in, well, before I jump back to there, we know that we're combining 3 of these strings in the combiner box. And when you do a parallel connection, amps increase. So by combining those 16.65 amps times 3 gives us 49.96 amps. Well, what wire do we need to handle 49 amps? Well, we're going to need 6 gauge wire down here, 55 amps. So jumping back to the whiteboard design, the 16.65 times 3 is 49.97 or so. So the wire coming out of here, the PV output circuit is going to be 49.97, and that's going to be number 6 gauge wire. This up here is 12 gauge wire. That comes standard. We're going to put 20 amp fuses in a combiner box. We're going to need a combiner box that can handle at least 3 strings. And now we're coming out with 6 gauge wire. Where's the next place we go to? Well, it's going to be a DC disconnect. What size DC disconnect do we need? Well, it's going to be carrying at least 50 amps. And normally what you're going to find is these DC disconnects are rated in 30 amp, 60 amp, or 100 amp, or even 200 amp systems. So we're going to need a 60 amp box if we're coming in, because 30 amps isn't going to cut it. We've got 50 amps coming in almost. So we need a 60 amp box. If we're going to put a disconnect or a breaker, or a fuse in here, we're going to need a 50 amp fuse. So the 50 amp fuse or breaker is going to go inside here if it's a fused disconnect. So we've sized that. Going from the DC disconnect, the next thing we go to is our inverter. All right, that's usually going to be inside the house or inside some sort of building. Did the wire size change or require to change coming into the disconnect and out? Well, the answer there is no, because it really is just an interrupt. So this is still going to be 6 gauge cable. And now we're entering in, and this is the inverter input circuit. Well, we've already determined that our inverter is 10 kilowatt hours, 10 kW, not hours, but just a 10 kW inverter. We've determined we need 2 of these. So when we design the system, we're going to duplicate it to this point. So we've got a 10 kW inverter. Well, how many watts are we coming in with? Well, we've decided that it's 24 panels and there were 415 watts each. So 24 times 415, we're coming in with 9,960. Okay, so we're fine, right? Not a problem. In fact, what we would find when we look at the spec sheet is if this 10 kW output is probably capable of taking in like up to 13,000 watts of DC in to send, that's using clipping to have 10 kW going out. We can double check that spec, but we're certainly fine because it's even less than 10 kW. All right, so that's all right. So what is the, we've already sized the voltage of each string so that it's not going to exceed. So the input there coming in, we're all fine. Now we want to size the wire going out, the PV output circuit. Well, how do we do this? Bear in mind, this is a 240 volt AC. Up till now, it was DC. In fact, if I look, I could tell you that under standard test conditions, the VMP over here was 40.9 volts. That's VMP. Times, we had 8 panels in a string. So, and the strings were balanced. So 8 times 40.9 gives us 327. So on a standard test condition day, we'd be operating at 327 volts coming in and leaving. Let's assume that we have to size it based on the maximum. So it's a 10 kW output. So I would put 10,000 watts divided by 240 volts. That's going to be AC. And we're going to end up with, divided by 240, 41.67 amps. But we have to now put in the safety margin again. That's the NEC. So we may multiply that times 1.25, and we're at 52.08. Now we don't have to put in the second safety margin because the inverter evens out any of the variability of solar. So now we're only dealing with the one safety margin. Now with this system, it just sort of happens that the amperage is going to be pretty similar going in and leaving. That doesn't always happen. And we also know from that table that 6-gauge wire can handle up to 55 amps. So we'll probably still come out of here then with that same 6-gauge wire because it can handle up to 52 amps. So where are we going to go? We're going to go to our AC disconnect. And once again, it's going to be either 30, 60, or 100 amp. Well, we're going to have a 60 amp box. And if we want to put some sort of disconnect in there, you know, some sort of breaker or whatever, well, we go to the next available size. I don't believe that they use 55 amp breakers or fuses. I think from 50 on, they're in 10 amp increments. But we could use a 50. We could decide to throttle down our system because again, this shows the safety margin. The safety margin only applies to wire. It doesn't apply to breakers or fuses. So we're anticipating we're probably only going to have a maximum of 42 amps. So I would probably in my design, go ahead and put a 50 amp fuse or breaker inside here. And that'll do us just fine. Okay, so then from here, we're going to go into our load center, our service panel. We're going to come in here And again, I'll just go with a 50 amp breaker. All right. Can we do this? Can we put a 50 amp in here? Well, that depends on the service panel. For a building that size, I'm going to assume that you've got 200 amp service coming in. So there's a 200 amp main breaker. All right, so remember the 120% rule. I'm going to erase some of this math here so that I can draw up in here and give you some calculations. I'll get rid of all of these over here too, just to get rid of some of the confusion. All right. Okay, so the 120% rule says that if the bus bar is rated for 200 amps or 100 amps or whatever, we can actually come in with up to 120% of its rating. So if we have a 200 amp bus bar and we, what's 20% of that? 0.2, that's going to be, let me see, 200 amp, 20% of 100 would be 20 amps. So we could have up to 40 amps coming in. All right. And we're wanting to come in with 50 amps. So that will present us with a problem. This system is too large to connect in load side connected to a 200 amp box. Now, if it turned out that the bus bar rating was 225 amps, which sometimes you'll run into, well, then we could go up to 65 amps, the 120% of 200 plus 25 more, and that would be okay. Or another option, let's say it's the 200 amp service, we could get, instead of a 200 amp main breaker, you could go ahead and put in like a 190 amp main breaker, and that would then allow us to go with a 50 amp connected breaker here. So those are some options, so that as long as from the grid and from the array, you do not exceed the 120% of the bus bar rating, then you can go ahead and install it. Alternatively, if you didn't want to do that, or if you, if your system, if your box was not big enough or had any empty spaces in it, then what we could do is notice from here, this is going to be your electric meter. Anywhere between here and here, we could tap in. This would be known as a supply side connection. And we could tap into there, and that gets into the 10-foot tap or the 25 tap rule. But the minimum issue that we run into is that the wire size here would, first off, the disconnect has to be at least 60 amps, and the rating for the wire has to be at least 60 amps. So we couldn't use number 6. We'd have to go up to 4 gauge. Minimum. I'd have to do the 25-foot tap or the 10-foot tap, but this would be our minimum. And the reason for that is because you'll see in the table, oops, that's not the one. That's what I want. Yeah, in the minimum, 4 gauge is going to get us to 70 amps. We need a minimum of 60, so we'd have to go with a minimum of 4 gauge there. But that might increase depending on the situation, depending on what the service is coming in. I don't want to confuse that too much, but that would be our situation where we could do a supply side connection, or we could change the breaker size here and come in here. But this is if there was only one. So yeah, I am going to confuse the situation because we made this thing more complicated. And I'm anticipating you guys are going to review this several times because I'm jumping over it pretty quick. So what am I going to do? I'm going to anticipate I've got to probably have a supply side connection on this. Because of the size of this, I'm actually going with 2 arrays. So this is going to be 3 strings of 8. And it's going to come in to another combiner box. So this will all be duplicated. And it's going to go to its own DC disconnect. So there'll be 2 disconnects. And then it's going to go to a second inverter. All of this replicating everything we just did down here. And then chances are we're going to bring these together and we're going to feed them in. There'll be some sort of junction box or something before this AC disconnect, but both of them are going to be feeding in. In fact, let me make that just so I don't confuse things. At this stage, we're going to feed those in to a junction box. This is going to be number 6. This is going to be number 6. And then from this junction box, we're making a parallel connection. Well, what happens with the amps is they increase. What was the amps that we had determined here? If memory serves, it was somewhere around 52 amps coming out of each of these inverters. You can get that either from the inverter spec or by taking the 10 kW, which is what the size was, divided by 240 volts AC, and then multiplying that times the safety margin of 1.25. All right, so if we've got 100, now we've got 104 amps coming out of the junction box into the AC disconnect. Well, 104 amps, that means we're going to need a bigger wire. We're going to need a bigger boat, right? All right, so 104 amps, we're going to need at least 1 gauge wire. So that goes to 110 amps. So from there, we're going to have 1 gauge. Remember, the smaller the number, the bigger the wire. Well, this 60 amp box, no longer any good. So we've got 101 amps. Well, that has our safety margin in it. We could probably get by with a 100 amp box, but let's assume not. So we're going to have to go out and we'll probably get ourselves a 200 amp AC disconnect. If I put a fuse of some sort in here or a breaker, I'll go with like a 110 amp breaker or fuse in here. And now, of course, the wire that's leaving here is going to have to be at least 1 gauge, maybe bigger. And we will have to do a supply side connection. That just basically means you're going to have to hire an electrician, come out, cut the wire somewhere between the meter and the main distribution, the circuit breaker box, and put in a bus bar of some sort and connect in there. You can't do it on the other side of the meter because, of course, then you'd be feeding your power out to the grid without getting any credit for it. So this is a pretty complicated system because it's a pretty big system. We could make it a lot less complicated by doing some things such as using SolarEdge and power optimizers, and we can size it, we could redesign it, and that's probably what I would do in the real world. But I wanted to show you string calculations, and we needed a string inverter in order to do string calculations. The one other thing that we should probably do while I've got this drawing up here is to say, okay, well, what about voltage drop? Will this wire be big enough to handle voltage drop? Well, let me go ahead and hit the stop share there, and let's look back at at Google Earth. Okay, so Ursula, is it possible for you to turn your mic on and let me know that this is in fact the facility that you were asking me to take a look at? You there at all? Okay, I'm not getting a response, so I'm going to assume that it is. And let's assume that service entrance and whatever, we can look and we've got some fairly good sized distances here. But I'm going to go ahead and just throw in some estimates. All right, so if I want to throw in some estimates, well, the one that we're worried about primarily is how far is it from the array to where we're going to house all the equipment. So let's
Jay,
just,
I'm here. I just I have dogs in the room, so
okay. Yeah.
yeah, that's our place.
Okay, good. And what kind of facility is it? I was guessing some sort of animal processing thing or a farm or something.
Farm, so small dairy and livestock, horses, horse barn, but we're looking to put to process some small animal feed on there. So we'll have some equipment like heat pumps for dehydration units, and there is 3-phase from this cooperative.
Okay.
But we don't, I mean, we are barely, like literally barely using power, and because the barns don't have any, the barns where the animals are at right now are not, they have power, but it's not being utilized at all. So the
Okay.
electric bill, we don't really understand why it's always so high.
Do you have
guess-
all electric like heating and air conditioning in the house?
Well, we had, so it was propane, and the farmhouse is gutted right now, so that's not even being heated. And then we have 220 electric heaters in the wintertime that we barely run because we converted all to wood, because we're like, where's all this power coming from? So we're basically down to like a refrigerator, freezer, lights, well, which might take power, electric water heater. But I don't know where the draw is coming from.
Do you have water heating buckets for the animals?
No.
Okay, yeah, that's definitely a very high bill for what you're describing. What you might want to do is have an electrician come out. It's possible that you might be simply having a ground fault that's feeding directly into the ground. You might be just using electricity that's doing nothing more than going into the earth.
Oh, wow. Okay.
So yeah, I do an assessment. I try and track that down because you're using about almost 3 times what a normal household uses.
Okay.
So yeah, and that's something that a solar system, if you had one installed, would have a ground fault detection device, and it would simply shut off as soon as it realized there's a ground fault. But if you ask an electrician to come out and try and track down where the power usage is, that'd be a good investment because you're spending a couple $100 a month on power you might not be using. So, okay, so I'm going to assume where in this picture is your, well, do you have separate meters, one for the barn and one for the house, or is it all on one unit?
So there's the big barn in the back is a separate meter. And then there's a meter for the house. But there's 2 sections to the house. The front part is an old farmhouse, and then the back part was an addition that, was like a separate apartment, I guess, area for their in-laws. So there's the electricity is fed to 2 different boxes in the one in the old farmhouse, one to the, new add-on in the back. And then there's a separate meter for the big barn. So that does have a separate meter.
And is there is the bill I was looking at the one for the house?
Just for the house.
Okay. The only reason I'm going to mention to you, just to file away in your brain, is the U.S. Department of Agriculture has what they refer to as REAP grants, renewable energy somethings. They'll pay up to 25% of the cost of the installation of your system as a grant for rural businesses. So the fact that your barn is separately metered makes you eligible so that when you go to install that system for the barn, the government will pay a quarter of the cost of it, which is really good. So, so don't forget that. But it won't apply. It won't apply to your house.
REAP.
Yeah, REAP, the REAP
Okay.
grant. Yep, I can get you more info on that, but yeah, it's available. It's an annual thing. It's part of the Farm Bill. So that money is available and you can apply for it. And you know, that'll help you out a lot. All right, so let's jump in. Well, on this unit here, I had decided you were going to put in a ground mounted system. You could put it on the roof, but you've got so much land there, you may as well have some covered parking or whatever. Do you know where the meter is on this facility?
So the meter would be to the right of your arrow.
Right down in the front of the house here?
I'm sorry, the other side of the house, almost directly on the other side, right there.
Okay, right in here.
Right in
Okay.
there.
And you could put the array over here if you wanted to, facing south, or you could put it over here for parking, doesn't really matter. Okay, so that gives us a fair idea. So let's assume we're going to put the array over here. So I want to put a 120 feet or so in there. So I'll jump back into my whiteboard and calculate the voltage drop. So the string, this calculation we would do as part of ours, but it's going to be so short, your combiner boxes are going to be under the array. So it's going to be like 10 feet or less. So the one we're worried about is going to be right here. And let's say it's 120 feet from your combiner box to your DC disconnect. And the DC disconnect in this case has to be within 10 feet of the inverter. So all of that will be co-located together. Typically, we'll put this on the outside of the house. The inverter might be on the inside of the house, or it could be on the outside. Either way, it doesn't matter. All right, so voltage drop. If you remember, voltage drop equals the amps, and in this case, the IMP, times resistance times twice the distance divided by 1,000 feet. Okay, so what is the IMP? Well, in this case, we're going to have to go back to the solar panels. Screen share. All right, solar panels here, and the data sheet, there were the 415s. So the IMP 8.13. Am I reading this right? Here's that. Oh, here's the IM. Where's the, oh, here it is, 10.15. 10.15. Okay. So we know our amps for each string is going to be 10.15. But we also know there are 3 strings. So that's going to be times 3 because they're a parallel connection. So that's going to be 30.45 amps. Let me get this out of here. Okay. All right, so 30.45 amps times the distance. I know I've just determined it's going to be 120 feet. So twice the distance is going to be 240 feet divided by 1,000. So it's going to be 0.24. And now I just need to know what is the resistance. Well, we also determined that we're going to be using 6-gauge wire. So in your book, there is a table, but I don't have the book up here. So let's look online, see if I can find a quick little Google search. I think I need Google Earth anymore. So resistance. Okay, and it's telling me the resistance gauges of 6-gauge copper. All right, not going to show me. Wire gauge is 6-gauge. Ohms per 1,000 feet is Looks like it's about 0.395. 0.395, okay. So we go in. So I've got 30.45 times 0.395 times 0.25240. So it's 30.45 times 0.395 times 0.24 gives us 2.88 volts. 0.88 volts for that particular section of wire. So from the combiner box to the DC disconnect, we're going to lose 2.88 volts. We would do the same calculation for every section here throughout. We could do it for the PV source. We could do it for the inverter input. We could even determine it all the way through here if we wanted to, or we could guesstimate. But I'm showing 2.88 volts and 327 volts is what we're operating at. So clearly the long run there is going to generate less than a 1% voltage drop. Because if I put that divided by 327, that's going to be, somewhere 0.9, I'm guessing, percent. So voltage drop isn't going to be a problem, but that's how you would go ahead and calculate it. Just as a rough rule of thumb, anything less than 200 feet, generally you're not going to have a problem with voltage drop, because in order to get your wire big enough to handle the ampacity, it'll be big enough to deal with any particular voltage drop issues. All right, so I know I ran through this very quickly. This is perhaps not exactly the way I would design it in the real world, but it gets you all of the math except for battery bank stuff. We'll try and touch on that in maybe one of the other sessions between now and then. Next week, we'll meet 1 o'clock on Tuesday, and then again 1 o'clock on Wednesday. Try and get through the rest of the book, chapters 8, 9, 10, and 11, all right? If you have any questions about any of this stuff, send me an email, and I'll either talk to you by phone or by email or whatever, or even Zoom if we need to. Okay, well, we're over an hour here, so I'll just cut it off here, and we'll meet again on Tuesday. Ursula, you have anything?
No, just thank you very much.
No problem.
My dogs say thank you too.
Okay, take care. Bye-bye.